All right, so we started doing rates and graphs and all these things, and then we realized that we needed more practice on linear equations. So we stopped. We did linear equations for a couple of weeks, and now we need to go back to rates and graphs. So I thought it would be appropriate to review a little bit before we get going because just to have a review because it's been a couple weeks and this is new information. So if you remember, we have a rate. A rate is something usually in a certain amount of time, not always. Um, but often a certain amount of time. And rates are really, really useful in real life applications for like, how long is it going to take me? How much is it going to cost me? How much, and all these different things. For example, let's say you're saving up for a bike and you've got a little job, right? And you get $45 per $45 every 5 days. So $45 every 5 days at your job. Every 5 days that you work, you get $45. Okay. So first of all, we need to figure out your rate. It's all great that you're getting $45 for 5 days, but it's really a lot more useful to know how much you're getting for one day. So we put it in a ratio. We have $45 for 5 days, and we just divide. We say 45 divided by 5, that's $9 per day. Now remember, 9 means for each. For every day that you work at your little job, whatever you're doing after school, you get $9. Okay. So you're saving up for a bike, and your bike is $486. It is a nice bike and good for you for saving up for it. Okay. How many days are you going to have to work at your job to get $486 for this bike? Well, we need an equation to be able to do this. Say, so we've got money, right? We have money and we have time, right? So we can set up an equation. Maybe you're looking at two bikes and one is $486 and the other one is $210. And you really, really want the $486 one, but you also don't want to be saving until you're 95 years old. If you can get the 210 one, maybe by the time the school gets out, you might get that one. And then maybe not get the 486. You're trying to decide, right? This is totally real life stuff. So it's $9 a day. We have money and we have time. Okay. So let's say we want to set up an equation. Money is in the numerator, so it's going to go on the left side of the equation. The amount of money that you have is going to be equal to your rate of pay, which for you is $9 a day, and go you. $9 times the amount of time that you're working, the number of days. And we're going to go ahead and call it T. Okay. And I'm using the loopy on my T so it doesn't look like a plus sign. Just kind of be aware of that when you're writing your stuff. So let's say I can do this two ways. Let's say how much, if I work for 2 weeks straight, which is 14 days, I'm going to work every day of the week because I'm a wild person, right? If I work for 14 days, how much money am I going to make after 2 weeks? So I can do that. I can say money is equal to 9 times 14. Okay, well, 9 times 7 is 63, and 63 times 2 is 126. So I'm going to have, at the end of 14 days, I'm going to have $126, okay? So I can figure out that. I'm going to use my units, so I remember it's $126. Or I could put in this for money and figure out how much time it's going to take me. I can go both directions. So how much time is it going to take me to save up $486? So $486 is going to be equal to 9 times the time. How many days am I going to have to work? Okay. Well, I have a 9 times t. The opposite of multiplication is division. And so I'm going to divide by 9 to get this t alone because I want to know the time, and divide by 9. So I have 486 divided by 9, which I'm going to choose to not do in my head. So 486 divided by 9 is 54. I'm going to have to work for 54 days to get bike number 1. So 54 days to get bike number 1. How much am I going to have to work for bike number 2? Okay. So I have 210 equals 9 times the time. Because I have the same rate, I'm still making the same amount of money, right? So I'm going to divide both sides by 9. Divide both sides by 9. So I have 210. 210, this one's not going to be as pretty, divided by 9 is 23.33. So I'm going to have to work 23 and about a third days to get this bike. 23.33 days. So I'm looking at this and I'm like, okay, so like here, I was a wild, crazy person. It's 14 days. I really don't want to work every single day of the week. Maybe I just want to work weekdays. So this is about a month. This would take me about a month. And this one would take me about 2 months, a little bit more than that. And so I have to decide, okay, so it's February, trying to do all of March, all of April. If I work really hard, I could totally have this bike by the time summer vacation starts. And that's kind of a decision you can make. But now you have the tools to make that decision. You know, I'm going to have to save up for 23 days for the one bike, 54 days for the other bike. Is it worth working for 54 days for the fancier bike? Maybe it just has better paint. Maybe better paint isn't worth it for twice as much work. But this enables you to make that decision. So we're going to flip over, and I want to look at some from our assignment here. So we're going to need to share screen again. I just have to change how I'm sharing the screen. And we're going to look at our assignment. We've got Cosette, and Cosette is walking, okay? Cosette is walking to her friend's house, and it's 2 miles away. And it takes her 35 minutes to walk there, okay? Which isn't bad. Cosette's going at a decent pace. She's not moseying by any means, okay? What is the rate of Cosette's walking? So we first need to figure out the rate. So we have distance. We have time. We can figure this out. And it's just going to be distance divided by time. So it's 2 miles divided by 35 minutes. I'm going to remember my units. Miles divided by minutes. And that equals, I have no idea. I have no idea what 2 divided by 35 is. Let's find out. 2 divided by 35 is 0.057. I'm actually going to keep that 7. 0.057 miles per minute. So every minute that Cosette walks, she goes 0.057 miles. Okay, a little bit. It sounds small. When you think about it as miles per minute, it's not too bad. Use the decimal equivalent to write a 2-variable equation to describe how many miles D Cosette can walk in how many minutes T. So, okay, look at this. D, that's distance. Distance is my miles. It's going to go on the left side of the equation. Distance is going to be equal to my rate, which is 0.057, times the time, however many minutes she walks. Okay. Now I can use this equation to figure out how far she's going. So distance is equal to 0.057 times the time. All right. So now we have to choose. Do we want to graph how far she walks? Or do we want to graph how long it takes her? And it doesn't matter. So I'm gonna do time. After 10 minutes, how far has she gone? So distance is equal to 0.057 times 10, which is going to be 0.57. Whoops, I added that in the wrong place. So 0.57. So after 10 minutes, she's gone a little bit more than a half a mile, which, you know, that makes sense. So how long has she gone after 20 minutes? The distance is equal to 0.057 times 20. And I know that if I double this, I'm just going to be doubling this. So that is 1.14 miles. Let's do some bigger numbers. What if she walks for 100 minutes? Go, Cosette, go. The distance is going to be 0.057 times 100. Okay, well, 0.057 times 100 is just 5.7. So after 100 minutes, she'll go 5.7 miles. What about after an hour? 60 minutes. The distance is equal to 0.057 times 60. Now, this is not one that I am choosing to do in my head. So 0.057 times 60 is 3.42. So after 60 miles, she's gone 3.42, or after 60 minutes, she's gone 3.42 miles. And then last one, I don't know, should we do 45? After 45 minutes is a decent time for a walk. The distance is going to be equal to, same thing, 0.057 times 45. And once again, I have absolutely zero desire to do this 0.057 times 45. I don't want to do it in my head, so I am choosing to not. 0.057 times 45 is 2.565. I'm going to round that to 2.57. 2.57 miles. So now I need to graph these. I need a graph, okay? So I'm going to have to flip back and forth. At 10 minutes, she walked 0.57 miles. So at 10 minutes, my x is 10. She walked a teeny smidgen more than a half a mile. So I'm going to put a little dot right there. Boom. Exactly, precisely 0.57. Yeah. At 20 minutes, she walked 1.14 miles. So 20 minutes was 1.14. So it's just a teeny smidgen above 1. Okay. Exactly perfectly right there. It's not going to be perfect, and that's okay. So at 100 minutes, she walked 5.7 miles. So we go down to 100, and you 5, and it's almost to 6, but really not quite. It's kind of almost halfway between 5.5 and 6. So right, boom, precisely, exactly right there. You guys wish you could be as precise with your graphing as I can. I'm not precise at all. I'm doing my best, but do your best. I mean, do your best. If it's way off, I'm going to mark it wrong. But if you're close, that's good. So after an hour, she's gone 60 minutes. She's 3.42. So a little bit less than 3.5. So 60 minutes. There's 3.5 right there. And then right below 3.5. I hope you guys can see my cursor. I have no idea if my cursor is recording. I hope it is. And then at 2 point, or else you guys are going to be like, see right there. And you guys are like, Mrs. Barlow, we don't see it. But I don't know. I can see my cursor. Hope you can. After 45 minutes, she's got 2.57 miles. So we got 45 minutes on the x-axis, 2.57. It is just a hair above 2.5. So right there. And when I have these all graphed, if I've done it right, they should make a line. If I have a point that's clear up here, then it's wrong. But I can know that, go, oh, I had a grave math error. I forgot how to subtract, or I lost my negative, or something happened, right? We have grave math errors all the time. It happens. And the nice thing is with these graphs, you've got a great does it make sense test, because if it's not on the line, it is wrong. So I know that at 0 miles, 0 minutes, she'd gone 0 miles. And these should, if I graphed them right, all be on the line. And we're pretty close. We're not exact, but we're close enough. What's wrong with this one? 40. Oh, I know what's wrong with that one. It's okay. So look, I made a mistake. Oh, awesome. And I caught it because it's not on the line. Oh, I love that. So it was supposed to be, look at this. It's supposed to be 45 minutes and 2.57 miles. But look, I accidentally graphed it 40 minutes and 2.57. And if you come over here to 45, boom, it's right there on the graph where it should be. So I've got this point right here that's not on the graph because why? Because I made a mistake. I love that we caught me making a mistake by the graph being wrong. That is what I want to happen to you. So I'm going to erase this. And my mistake is gone, and it's like it never happened. But that's exactly what I want you to do. I want you to look at this, and then you draw your line, and it's like, oh, something is not right there. And then you look and you're like, okay, so why is this not right? And it's not right because you made a mistake and it's actually legitimately not right. I made a mistake when I was graphing. Oh, that makes me so happy. I mean, I'm not happy that I made a mistake, but I'm really, really happy that we caught my mistake and that you were able to see that happen, because I guarantee you, okay, so I'm a math teacher, right? Like, I do math for my job. They pay me money to do math. And it's probably a nightmare for some of you. I don't want to do math, but they pay me money to do math, and I think it's probably reasonably safe to say I'm kind of okay at math, right? So so if I can make a mistake doing math, you can make a mistake, and it doesn't mean you're not good at math. It just means that you're a human and humans make mistakes, and we can catch those mistakes. And I love that that happened. Let's move on. All right, using either the graph or the equation, how long would it take Cosette to walk 11.75 miles to her grandma's house? Woo! Go Cosette. She is like in it for the long haul. We're walking to grandma's house like almost 12 miles away. But okay, so we're going to assume that Cosette walks at a constant rate, because we're going to say that Cosette is not going to get tired. She's not going to stop at crosswalks, right? She's not going to... There's going to be no traffic in her way. She is just walking, and go Cosette. So there are a lot of assumptions here, but we can come pretty close. So here, okay, so up here, we had time, we had time, we had time, we had time. We put time into the equation, and we got distance out on the other side. Here we have distance, and we need to get time. Can we do that? Yes, yes, we can do that, because weird things just happened to my graph. Okay, we have the distance is equal to... what was 0.057 times the time. Okay, so now I know distance instead of time, but I can solve for time, because we've just spent the last like week and a half, week and 3/4, 2 weeks, whatever, reviewing linear equations. We can solve linear equations in our sleep. If you're like me, you just might solve linear equations in your sleep. So the distance, she's got 11.75 miles to get to grandma's house. And that equals 0.057 t. Now I want to get this t alone. So it's multiplied by the 0.057. So to get it alone, I do the opposite of multiplication is division. So I'm going to divide both sides by 0.057. It's just the same thing we've been doing. 0.057. Sometimes I choose to not do math in my head, and sometimes I am not able to do math in my head. This is one of those times. I am not able to do this in my head. I'm also not able to cross my t properly, because I tried to turn it into the equal sign. Don't think you guys got that. Okay, so I have 11.75 divided by 0.057. So let's pop up our calculator. 11.75 divided by 0.057 is 206.14. Now, okay, so 206.14 what? Units are important, especially one of these. Okay, so it's time. 206.14 seconds, 206.14 years, 206.14. Let's remember, what was our rate in? Our rate was in miles per minute, so our answer is going to be in minutes. It takes her 206.14 minutes to walk to grandma's house, which, okay, when you think about it, that's a little bit more than 3 hours, a little bit more than 3 hours for 11.7, like almost 12 miles. Completely not unreasonable. This is this answer makes sense. It's going to take her almost 3 hours is, well, shoot, 3 hours is 180 minutes. It's going to take her almost 3.5 hours to walk almost 12 miles. Yeah, that makes sense. Go Cosette, go. She's going to get tired though. But anyway, so the second one is exactly like that, except Frank's in a hot dog eating contest, and we're pretending that Frank gets neither tired nor full. He does not vomit. Frank is a hot dog eating machine. Okay, so pretend Frank doesn't get full. And then down here, we're just going to have some linear equations that we don't have the rates going on with them. And then we're just going to graph the linear equations. They're a little bit simpler. Okay. Not a lot to this, because I don't want to take you all day. We're just reviewing, and then we're going to do new stuff next week. Anyway, have fun. Holler if you have any questions, as usual, which you guys never do. But, you know, I'm here if you do.